Hi, hello, welcome to part 2 of chapter 7 lecture. In this section, we are going to discuss topic called molecular polarity and molecular geometry. And before I discuss these topics, I just want to take you guys back to chapter 6 and remind you guys what we discussed there, because it is very important for you to understand and make a connection with the topics that we discussed in chapter 6 under electronegativity and polarity, and so that you can apply them here seamlessly and understand what is going on. So let me do a quick review of what we discussed in chapter 6. In chapter 6 under electronegativity, we discussed the behavior of atoms to attract towards itself in a bond, and we call that as a electronegativity. And we have a scale, and these are the numbers that we looked at, different electronegativities. And here is the chart that we looked at, how electronegativity varies with the atomic number. And we defined bonds as either a pure covalent bond or polar covalent bond or ionic bond based on the differences in electronegativity of the bonded atoms. And we said that electrons could be stayed in the middle for non-polar covalent bonds, and electrons stay on one side of a electronegative element in a polar covalent bond. And we said in ionic bonds, electrons are completely on negatively charged ions. This is kind of what we discussed. And we also have these ranges of electronegativity difference between 0.5 or less, called as non-polar covalent bonds. And we said if it is the electronegativity difference is between 0.5 and 2, we call those types of molecules as polar covalent molecules. And we said if it is above 2, we call those types of molecules as ionic. This is kind of summary that you need before we start discussing chapter 7, which is what we are going to do right now. So coming back to here. So what we just did in chapter 7 so far is we learned the topic called molecular geometry. Under molecular geometry, we learned that atoms or electron pairs or electron domains distributes around the central atom to avoid the repulsions according to valence electron repulsion theory, the VSEPR theory, so that molecule is stable because it's not going to bother central atom with too many electrons nearby each other. So when it does, the molecular polarity is going to be, let me recollect my words. So the molecular geometry is an important factor in determining the molecular polarity of a molecule. Let me say that. Molecular geometry has high importance in determining the molecular polarity of a molecule. Because what you know so far about polarity is you only know to find if a bond is polar or not. When I give you a bond with the two atoms, so far you know that you have to identify if that bond is a non-polar covalent bond or a polar covalent bond or ionic bond. But what if a molecule is a part of what if a bond is a part of molecule? If it has multiple bonds, how it is going to affect the molecular polarity. That's what we are going to discuss now. The molecular polarity has the molecular geometry has a huge application in determining the molecular polarity, because the shape of the molecule is going to help us determine if the molecule is going to stay as a polar, even with the polar bonds, or not stay as a polar, even with the polar bonds. So we are going to dig deep into this topic to identify, starting with defining what is a polar bond is. If, as we discussed in chapter 6, if there are two atoms that are different from each other, made a bond by sharing electrons, or not sharing electrons also, like ionic compounds. Let's focus on covalent bonds where they share the electrons. And if they happen to have significant electronegativity difference, which is anywhere from 0.5 to 2 electronegativity difference, then they were the candidates to identify or qualify them as a polar types of bonds. So what if you have a polar bonds in a molecule that has different types of geometry? Would it affect the overall polarity of the molecule or not, is what we are going to learn in this chapter. So here is an example, right? This is just to remind you what we discussed in chapter 6. We discussed there that bond between hydrogen and fluorine is a polar bond because fluorine has huge electronegativity difference with hydrogen, so it takes the electrons away. And we learned how to show these electronegativity differences as delta negative and delta positive, and we know how to show the dipole moment with the crossed arrow, right? So I just got a little bit of list here to highlight the importance of knowing this topic, polarity in molecules. Why do you even have to know, right? These are, we come across these polarity, non-polar molecules in our daily life, but we don't even pay attention to them most of the times. But even if you start doing that, it is a beautiful thing. Simplest thing, before I look at the list, just think the basic information. Why the water does not dissolve in any cooking oil? What's the difference between them? The difference between them is one is polar, one is not polar. Water is polar, oil is not polar. Here are some other examples that you can easily read and try to see where the polarity is playing between when you mix these mixtures. Like cream of tartar, a polar compound is added to egg whites, which contains polar proteins, which helps them to form, form foam between them when you beaten them. And fruits, well, any fruits like apples or avocados or some other fruits, when you cut open them, you will notice that they will start browning after a certain time, even in a couple of hours. It is because the polar molecules on the top of the cut open fruit will react with oxygen, and it is because of the presence of the polar molecule enzyme known as polyphenol oxidase, polar compounds. They were everywhere. Why it became a polar molecule is because it contains polar bonds. And other examples like very common. But when you poach the eggs in water, you always add some vinegar to it so that the egg that you're trying to poach wouldn't just become like a slurry and become like a feathery tail. So it stays as nicely poached egg. So these are some examples of applications of polar molecules. So there is some incentive to know about the polar molecules other than just scoring points here. Let's see what we got here. Oh, let me put everything that I have. Okay, looks like animation didn't work as planned. See, this is everything that I got here. So let's read from top. The polarity of a molecule made up of 3 or more atoms depends on 2 things. Those 2 are very important to determine if a molecule is polar or not. So first condition has to qualify for even you to check the second condition. The first condition is that polarity of the individual bonds. You need to have at least one polar bond. If you're going to consider a molecule as a polar, you need to have at least one polar bond. Then you will check the condition 2 to see if the molecule is going to be polar or not. That is molecular geometry. What I mean by molecular geometry is the molecular geometry is going to cancel out the polar bonds. That's what I mean by molecular geometry. So there are 2 things that you need to check. One is if the molecule has at least one polar bond or not. And second one is the molecular geometry playing a role in canceling the polarity of the bonds or not? So let's go one by one. There is one easy case to identify a polar molecule, which is this one, first one. When all molecules are when a molecule has only one polar bond. That's the easiest way to identify if a molecule is polar or not. So if a molecule has no polar bonds, the molecule is not polar, easy to say. If a molecule has one polar bond, yes, molecule is polar because it has at least one polar bond. So it is a polar molecule. The complication comes when a molecule has more than one polar bond. That is when you need to check the molecular geometry for cancellation of the polarities. And it only happens in symmetrical molecules, which means, all sides of the molecules are looking, same. Let's look at this example of carbon dioxide for that. So in this example of carbon dioxide, you have carbon in the middle, oxygen on both sides. You can see the similarity, right? Molecule looks symmetrical. It has two oxygens on two opposite sides, and it has the geometry of linear because it has two electron domains around carbon. So it has linear geometry. They were separated by 180 degrees angle. So as a result, the dipole movement towards oxygen on right side is canceling the dipole movement on the oxygen on the left side. As a result, the molecule as a whole will become non-polar. This is what you need to get. The carbon dioxide molecule has a polar bonds because the electronegativity difference between carbon and oxygen is significant, greater than 0.5. But CO2 molecule has symmetrical bonds on both sides that were completely opposite to each other, that were canceling the dipole moments on right side with the left side. So as a result, CO2 molecule contains polar bonds, but the molecule is non-polar. Okay? This is the trickiest one to get. If you get this one, rest of the problems are going to be easy. Again, let's look at these rules. You need to check these rules every time. That's why I included the rules in every one of the possible problems that we are going to work in this lecture. So to identify the polarity of a molecule, I'm going to say this many times because it has to stick with you. If you already get it, don't get mad at me because based on my experience over the years, students might overlook sometimes. So I don't want you to overlook again. So to identify if a molecule is polar or not, first you need to look for if there is at least one polar bond or not. Then second, you need to check the role of the molecular geometry. Is it helping to cancel the polarity of the symmetrical bonds or not? So let's look into another example again. Let's say what do you say about water? Is water polar or non-polar? So water has the molecular geometry of bent. So two hydrogens are in a bent shape, like 109 degrees angle, like going down like this, but away from each other like 109 degrees. As a result, even though there is a symmetry in bonding, they were not really going in opposite directions like in CO2. They were kind of going in their own direction, but not in a way to facilitate the cancellation. So as a result, because EY is not equal to EZ, H2O molecule contains polar bonds, and this molecule is also polar. So H2O molecule is an example of molecule containing polar bonds that is a polar molecule. Okay, let's look into this example again. Again, I included all of this same information again and again because you need to respect the data. You need to check these steps to get the final answer. We are going to work on molecule called boron trichloride, BF3. Work on it if you can by pausing the video, otherwise you can watch the video right here. So BF3 contains 3 electron domains around it, and it contains 3 fluorines, and 3 fluorines has the molecular geometry of trigonal planar. Trigonal planar separates each of the fluorines 120 degrees angle away from each other in a perfect 120 degrees angle difference in a trigonal planar shape. As a result, the cancellation of the dipole moment easily happens. Each one of these oppositely dipole charges are getting cancelled by each other. As a result, the BF3 is a molecule that contains polar bonds. BF bond is a polar bond, but whole molecule is a non-polar molecule. Let's look into one more problem. Let's look into a problem called CCl4. Okay, and I need you to answer that before you watch the video. Carbon connected to 4 chlorines, so it has 4 electron domains. So it has a molecular geometry of tetrahedral. Tetrahedral again contains 4 chlorines that are going in all 4 directions that were canceling each other due to the symmetry in its molecular structure. As a result, CCl4 contains polar bonds, but molecule is non-polar. Okay, that's how you need to come up with the answer. You need to see if the molecule is just containing no polar bonds, so that you can call it as non-polar. You need to see if a molecule contains only one polar bond, so that you can call the molecule as polar. Then comes the tricky version, where molecules contains more than one polar bonds. That is when you have to check the molecular geometry, check for the symmetry to see if you can cancel the dipole movement on opposite directions. If not, then you can call the molecule as polar. So that's kind of steps you need to do. Let's look into this problem called CCl4. So in this example here, CCl4 contains 3 chlorines and 1 hydrogen. So you can clearly see that there is no symmetry here. Symmetry is lost because not all of the atoms are not same. There is one CH bond that is no match to Cl bond dipole movement because it only contains 3 polar bonds and 1 non-polar bond, which is CH. So you have differences in electronegativities between bonds that are going in opposite directions, which means CHCl3 is a molecule that contains polar bonds, but the molecule is also polar. Okay. All right. Let's look into this problem. It's a short lecture. We are going to wrap it up pretty soon. Determine whether PCl5 is polar or not. What do you have to do? You have to draw the Lewis structure first, so that you can clearly see what types of bonds are present in PCl5, and then you will identify if those bonds are polar or not. If they were not polar, you don't have to go further. You can call molecule as non-polar. But if they happen to be polar, then you need to look if there are cancellation of charges, cancellation of dipole moments or not, to determine if the molecule is polar or not. All right. So plan, draw the Lewis structure. That's the Lewis structure of PCl5. And now we are going to identify if the bonds are polar or not. PCl bond is a polar. It has significant electronegativity difference. As a result, we are going to check for the molecular geometry for the cancellation of the charges. So molecular geometry of PCl5 is trigonal bipyramidal, right? Trigonal bipyramidal. So it has a trigonal planar structure in it with 3 chlorines. So there is a symmetry, and also it has a linear structure from top to bottom. So these 3 chlorines that are in the trigonal planar structure are going to cancel out each other, and these 3 chlorines that are unlinear to each other are going to cancel out as well. As a result, all PCl polar bonds are getting cancelled out each other by its opposite counter symmetrical PCl bonds. As a result, PCl molecule is a molecule that contains polar bonds, but molecule is non-polar. Okay, let's look into one more problem. H2CO, where carbon and oxygen are double bonded to each other. Is it polar or not? Again, draw the chemical structure. It already gave you the clue. Carbon and oxygen has a double bond. So hydrogen obviously has to go to hydrogen, which means there is at least one polar bond between CO. There is your polar bond. And do you see any symmetry? Well, you don't even have to go there. There is only one polar bond, and the rest of them are not. So a molecule with one polar bond will be automatically called a polar molecule. You don't have to overthink it. Let's see if I got more. So it's a summary, right? If a molecule has only one polar bond, that's the easiest way you can identify if the molecule is polar or not. The answer is it is a polar, right? Let's look into kind of an application of this topic. So we are trying to say that symmetry in a structure is going to result in if a molecule is polar or not. Sometimes you can use it to identify the difference between 2 compounds. One of such way is structural isomers. Structural isomers, we don't have to learn a whole lot about them in general chemistry, but in future organic chemistry, they were going to be one of the major topics that you would learn. So that's why I just included the definition here. Isomers are two different compounds, but with the same chemical formula and the same atom-atom connectivity. Everything looks same for them except how they were arranged in molecular geometry. One is arranged different from another, but same atom-atom connectivity. I'm going to show you the structures. What it means is, again, you don't have to worry about how to draw isomers, but now. So you could actually differentiate one from another based on dipole moment, based on polarity between isomers. So in this molecule, Cis-Dichloroethylene, two chlorines are on same side. So there is no cancellation of polar CCl bonds one from another. As a result, this molecule is polar because both chlorines are pointing same direction. They were not canceling each other. It contains polar bonds, the molecule is polar. However, the isomer of cis-dichloroethylene is a trans-dichloroethylene, and this molecule has carbon-chlorine bonds on opposite direction. As a result, the dipole moments of CCl bonds are getting cancelled out one from another. As a result, it became non-polar. One is polar, one is non-polar. Only difference between them, how they were arranged. That's all from this topic, molecular geometry and polarity. This is useful topic for, let's say, to understand the next topic called intermolecular forces. And also several times, especially in next semester solutions chapter, we are going to use these topics like polarity easily. When you make solutions, I'm going to ask you to comment on if it is possible to make a solution between these two compounds. The only way you can predict if it is possible or not by predicting molecules are polar or not. So in a way, it is important for you to understand how to predict a molecule polarity. Is it a polar or not? It's not too complex, related to section 1, which is large topic. So I hope you get it, and I'm gonna see you in next lecture.